أعزائي الطلاب، تحية لكم. أنا حسن كوراني، بعلمكم مادة الرياضيات لصف العلوم الحياة. بالدرس الماضي كنا بلشنا بالexponential function، وصلنا لequations and inequalities dealing with exponential function. In this lesson we are going to study the derivative of the exponential function, the limits of the exponential function, and we'll see some simple examples on it. Okay? First, I'd like to tell you that it's quite simple to find the derivative of exponential function, and I will show you the proof of what we are going to see. The derivative of ex, in fact, is ex. Why? We'll see the proof. If we let f of x equal ln x, we are going back to the inverse of exponential function as we said before. Then, if we have f inverse of x, and we show that f inverse of x is ex. If we call this y, and we need the derivative of y, the derivative of x, and we are going to show it ex itself. How could we do this? Well, we need the derivative of ex, that is the derivative of y. The derivative of ex, it will be the derivative of the inverse function, since it is equal to ex. As a formula we know from the revision we did before, it will be 1 over f prime of y, not of x. Now, what is f prime? F is the ln function itself, and f prime of x is 1 over x. 1 over x, so it will be 1 over y. F prime of y is 1 over y, which is y itself. Be aware y is equal to ex itself. Thus, or then, ex prime is y, so it is ex itself. By this, we prove this. Prove that ex is the derivative of ex. We need just memorize this formula, this rule, and this is for deep understanding for this result. The second case, general case, what if we have e to ux, the derivative of this equal what? Where u is a function of x. U is a function of x. Let's say it is 2x plus 3 or x squared plus 5x minus 1, whatever. To do this, we can put y equal EU. Before go direct to the derivative, we just make ln both sides. This is equivalent to say that ln y equal u. Now, deriving both sides of this equation, this helps to get the derivative of y, since we need, in fact, y prime equal what? We need y prime. By this way, implies that the derivative of y, since y is a function of x, in fact, since u is a function of x, then the derivative of ln u, or ln y, it will be y prime over y equal u prime. This is not constant, this is a function in x. So, by crossing multiplication, y prime, it will be u prime of x times what? Times y. Again, what is y? From the beginning, we put y equal e ux. Thus, you can easily deduce that y prime equal u prime of x times EU, where u prime, y is EU. This is the proof of the derivative of EU. As a conclusion, never mind, these details are just to understand very well, deeply, why we get this rule. As a conclusion, I advise you to memorize this, and you can apply these rules directly. What are these rules? There are two cases. Ex is its derivative is ex itself directly without proof. And the second case, general case, EU, its derivative is what? It's u prime EU itself. Again, don't miss these two main rules. Let's do some direct examples on these in order to understand what we have got here. One, again, I advise you to pause this video and try to solve it, do it yourself to get the benefits of this lesson. If we have, let's say, f of x equal ex squared minus 3x. What about if f of x equal ex squared minus 3x, what about f prime of x? Look at this. It has the form of what? It has the form of EU. This plays the role of u. According to the rule, it says that it will be u prime. So the derivative of this exponent, it will be 2x minus derivative of 3x is 3 multiplied by the function itself, EU. That's it. Okay? Now, a little remark, you must note that this is always positive. This helps to study the variation of this function later. And the sign of f prime will depend on the sign of this function. Clear? Let's see another example. What about if we have another function, let's say g of x equal 5x ex. What do you notice about this? This reminds us by what? We have 5x, it's not constant, it's a function, it's like u, and this is v. Isn't it? And let's recall that the derivative of uv is what? If you have two functions, product two functions, it will be u prime v plus uv prime, isn't it? Okay, let's do this then. G prime of x, it will be u prime, the derivative of 5x is 5 times v ex plus u itself, the derivative of ex, as the rule says, it's ex itself. Okay? You can leave it like this, or if you like, if you need to study the variation of this function later, g prime will be taking a common factor 5 ex, you'll get 1 plus x at the end, and this is also positive, and the sign of g prime depends on the sign of that expression, 1 plus x. Okay? Let's see another example for these, on these. Let's say, what if we have if f of x equal ex over x. Again, as you see, we have a function with numerator ex and denominator x. It's not constant. So this reminds us by the form u over v. This is u, and we consider this as v. And as you know, the derivative of u over v is, this is a formula, you should memorize it well. It will be u prime v minus u v prime over what? V square, yes. After that, we can find f prime of x. It will be u prime, the derivative of ex is ex itself, times v, we can put x here, minus u ex times v prime, which is derivative of x, which is 1 over x squared. After that, we can reduce this form to get x minus 1 with a common ex over x squared. Again, if you looking for the sign of this expression, this will be positive, and this is also greater than positive, should be, according to certain condition. In this title, we are going to study the limits of the exponential function, and we can see the curve of EX. This helps very well to memorize the limits of this exponential function. Well, before that, حابب لكم إنه exponential function behavior تبعها increases over minus infinity till plus infinity by this way. From minus infinity till 0, it increases just 1 unit. After that, it suddenly goes fast till plus infinity after 0, 1, 2, 3 by this way. وهالشيء بهالايام عم تسمعوا عن سرعة انتقال الكورونا فيروس للأسف يلي هو معنا بالبيت هالايام. سرعته جاي بشكل exponential manner, exponential behavior، لأنه مثل ما شايفين كتير في شبه بين الاكسبوننشال فانكشن وسرعة انتقال هذا الفيروس، لأنه minus infinity till 0 it just increases 1 unit. After that it increases very fast till plus infinity. طيب على كل الأحوال let's see the first limit as x tends to minus infinity of EX. Look at the curve. You can easily see that as x tends to minus infinity, the value of EX, it's very, very small. It's near 0, so the limit it will be 0. So we say that EX tends to 0. In fact, it is 0 plus. Okay? The second limit is limit as x tends to plus infinity EX. Try to guess the solution, the result of this limit from this curve. As you see, it's clear that as x increases till plus infinity, then EX increases also very, very fast to plus infinity. So the result will be also plus infinity. These are, in fact, the main two limits on exponential function. Well, there are two different particular cases that are very important and useful, especially in exercises and in tests, which are limit as x tends to plus infinity of EX over what? Over x. If you try to calculate this limit, you will get what? You will get e to infinity, infinity over infinity, which is, as you know, an indeterminate form. And this indeterminate form, infinity over infinity, and another case which is 0 over 0. In these two cases we can, as you know, allow L'Hopital rule. By L'Hopital rule, we can make derivative of the numerator and the derivative of the denominator, and we again calculate the limit. Plus infinity. As we know, EX, derivative of EX is itself, derivative of x is 1. So we get at the end what? Plus infinity over 1, which is plus infinity. So directly we can, this is the proof, and we can directly use it, limit of EX over x as x tends to plus infinity. We can directly put the answer as a rule without this proof. It will be what? Plus infinity. Well, in fact, I'd like to tell you that we can understand this in another way without using L'Hopital rule. How? If you look at y equal x, this is this function y equal x is of this curve. As you see, both goes to plus infinity. As x tends to plus infinity, x tends to plus infinity. Similarly, EX goes to plus infinity. But one of them, in fact, goes faster than the other. It's clear that EX goes faster than x. Okay? So, at infinity, somehow we can think about it in this way. This will be plus infinity, and this will be a number now somehow. Yani after, if x tends, let's say, to 100, this will be e power 100 over 100. E power 100, which is, if you use your calculator, you can't use your calculator since it is a very, very large number. So we say that this EX, the numerator, goes to infinity faster than x, Thus, the result will be plus infinity over number, so it will be plus infinity. Clear? Never mind, this is, you can directly use this as a rule. Another rule similar to this, which is limit of x over ex. Similarly, if you replace x here, you get plus infinity over plus infinity, which is again infinity over infinity. It's similar to that, but it is inverted. But in this case, ask yourself, who goes faster to plus infinity? Although they both go to plus infinity, but one of them reaches plus infinity faster than the other, which is the denominator, sorry. It will be constant over infinity. 100 over e100, 1000 over e1000. e1000 is a very, very large number compared to x. So we can directly say that the result will be one constant over infinity, as you know, it will be 0. Or you may prove this by using L'Hopital rule, as we saw before. Okay? Let's see some simple examples on these limits. Before that, sorry, I'd like to tell you a small remark. Similar to these last two cases, if we have limit as x tends to plus infinity of x power n over ex, even if we have x power n, it still goes to plus infinity slower than ex. So the result will be number over very large number, it will be what? 0. Directly you can use this as rule. For example, for instance, if we have limit as x tends to plus infinity of x squared over ex, x power 3 over ex, whatever, the result directly we can put it as a rule as 0. Another remark, similar to this but inverted, try to think about it. Okay? In this case also, ex is very fast, goes very fast to plus infinity. Thus, the result will be plus infinity over number, which is another rule we can manipulate it or use it anywhere in exercises. Okay? These all about the limits. Let's do some examples. I will give you 4 examples. Calculate the following limits. These are some samples that help us to understand very well these rules of limits. Let's say in the first example, I'll give you, if we have limit as x tends to plus infinity of ex over, let's say, 5 minus x squared. If you try to find this limit, you will get, if you substitute a limit of ex, it will be plus infinity over 5 minus plus infinity, it will be minus infinity, as you know, which is the case of if. In this case of indeterminate form allow us to use L'Hopital rule. By L'Hopital rule, as you know, we keep the same limit and we make derivative of the numerator and derivative of the denominator. Don't miss, it's not the case of u over v. It's L'Hopital rule says that we make the derivative of the numerator and the derivative of the denominator, which is derivative of ex is ex and the derivative of the denominator. This is 0 and this derivative of this minus 2 over what? X. As you see, this term remind us by what? By this rule, we can directly use it, and don't miss this negative number. This will be plus infinity multiplied by 1 over minus 2, which is in fact minus half. We were in indeterminate form, we got a result which is minus infinity. Limit as x tends to plus infinity is minus infinity. Let's see another example to understand very well these limits. Second part, limit as x tends to, let's say, plus infinity of x cubed, let's say minus ex. Well, the first step, usually we substitute x by plus infinity, or let x goes to plus infinity, the same meaning. You will get plus infinity cubed, which is plus infinity minus e to infinity, which is infinity. As you saw, it's not zero, sorry. Sure, this is if case. And this if, in this case, we cannot use L'Hopital rule, as you know. L'Hopital rule is just for the cases infinity over infinity or 0 over 0. What should we do in this case? In fact, usually try to change the form of this. Usually we take the common factor, as we take a common factor, and it's preferable to take ex, which is the stronger or the faster to infinity than x cubed, as we said before. This will be ex into x cubed over ex minus what? 1. Now, if you try to calculate the limit of this part as a rule, this goes to 0. As you see, ex is faster than x at plus infinity. This idea, just we use it in case we have limit at plus infinity. So at the end we get the result plus infinity, e to plus infinity. It will be plus infinity multiplied, don't miss this, 0 minus 1, which is minus 1, which is minus 1. This is the last result. Okay, clear? Next limit, we have 2 limits. What about if we have ex minus 1 over, let's say, 2ex plus 3? Again and again, we directly first substitute for limit, or let x tends to infinity. This will be infinity minus 1, which is plus infinity, over 2 times infinity, infinity, plus 3, which is infinity again, if, and this is suitable for what? Yes, for L'Hopital rule. By L'Hopital rule, again we make derivative for numerator. The derivative of ex is ex itself, derivative of minus 1, which is 0. 2ex, 2 is a constant, we keep it, and we multiply by the derivative of ex. The derivative of ex is ex, and the derivative of 3 is 0, so we just eliminated. At the end, before you, be careful, before you substitute x, just simplify these to get what? 1 over 2, which is the needed result of this limit. Clear? The last one is limit as x tends to, let's say, 0 of ex 2x, let's say, minus 3ex or plus 3x minus 4 over ex minus 1. In the first step, you can directly, as we did before in the previous examples, you can get e to 0, as you know, 1 plus 3e to 0, 3 minus 4, which is, over e to 0, 1 minus 1, which is the case of 0 over 0, which is again an indeterminate form, and L'Hopital rule in this case is allowed. By L'Hopital rule, making derivative of the numerator, as we said before, and derivative of the denominator. Then, be careful about your calculation in order not to get calculation mistakes. E to x. This reminds us by what? E to u. And EU, as you know, the derivative of EU, let me remind you by this, it's u prime EU, isn't it? So the derivative of e to x, the derivative of 2x is 2EU, not ex, e2x, plus 3 constant, we keep it. Derivative of ex is ex itself, and the derivative of that term is 0. So the denominator, the derivative of the denominator is ex minus 1, which is the derivative of minus 1, which is 0. At the end, as you see, again, don't miss this limit. You should write it, don't miss this, this term. Now, if you again substitute for 0, you will get 2 e to 0, 1 plus 3 e to 0, 1, so it's 3 over e to 0, which is 1. At the end, we get the result, which is 5. That's it. Well, the next title will be about the integration, antiderivative, or integral of exponential function. It's quite simple. We have just two cases, general cases. Okay. Antiderivative or integrals on exponential function. The first case we have integral antiderivative of ex dx. Think about the function whose derivative is ex. This is the fact of concept of integration. The function whose derivative is itself is what? Ex itself. Always don't miss this constant where c is arbitrary, any constant. We usually put it in when we are working on antiderivative. If you try to make the derivative of this, it will be ex, so this is an antiderivative, or this is the antiderivative of ex. Particular case, if we have e to exponent ex plus b dx. Look at this, where a and b are two real numbers. The antiderivative of this will be what? 1 over a, you can directly use it, ax plus b, and don't miss plus c different from that, or you may call it k or whatever. The third case, generalization for this or that, it will be integral of u x dx, where u is a function in terms of x. Here we should have a term which is the derivative, in fact, of this. We should have it. Sometimes it's direct, and sometimes we must make some modifications on this term to get u prime. Okay? The derivative of the antiderivative of this will be eu x plus c. And if you check this, if you make derivative of this side, right side, it will be derivative of eu, as the rule says, it will be u prime eu, and this is it. Clear? Let's do some examples on these cases, and the lesson will be finished by this. Examples. If we have, let's say, example 1, or if we are asked to calculate antiderivative of e3x plus 2. This is, be aware about this, this is an indefinite integral. There is no boundary for x, so we are dealing with antiderivative, not the definite integral. It will be what? It's similar to the second case. It will be the derivative of this, which is 3, so it will be 1 over 3 e3x plus 2 plus c, don't miss it. Okay? It's direct. The second one, let's say we have, what if we have x squared minus 5 dx? Try to similarize this with one of these cases. As you see, we have here, we don't have here x, we have somehow something which we usually call it u. If we said that we should have here u prime. If you let u of x equal x squared minus 5, you can easily find u prime of x. It will be derivative of this 2x, and derivative of that is 0. Now, let's see these terms in this, or replace these terms in this form, in this function. Now, after we suppose that ux equal x squared minus 5 and u prime equal 2x, if you look at the given form, we have eu, it's clear, but u prime is modified. We have additional 2 here, as you see. How could we get 2? Or u prime, sorry. We can easily multiply it here by 2, and in order not to change the given, the value of the given, we should divide by or multiply by half. By this way, we didn't change the given value. But, so, let's change the form. Half, which is a constant, we can always multiply by constant and outside the integral, it will be 2x now, it is u prime itself, e to u dx. And clear that this helps us to know the antiderivative or an antiderivative of this integration, which is, don't miss this half, integral of u prime eu, as the rule says, it will be e u x plus c, where again we go back to the initial expression in terms of x, it will be ex squared minus 5 plus c. That's it. This is the answer of this integration. Let's see the next example. Let's do a definite integral from 0 to 1 ex 1 plus ex dx. When we have finite values, so the result will be a constant number, not a function. So now, if you look at this expression, ex over 1 plus ex, sure, we cannot make integration of the numerator and denominator alone. We have to deal with it as a whole function, this function. Well, try to, in this case, to think or guess who is the derivative of the other. It's clear that if you look at the denominator, has an additional 1, so this must be this is the derivative of this denominator. So we let u of x here to be 1 plus ex, and u prime, it will be derivative of this 0 and derivative of this is ex itself. So we can easily notice that this integral will be, it has a simpler form which is 0 to 1, integration from 0 to 1 of u prime, this is u prime, over u of x dx. And as you know, this reminds us by what? What function do we know from previous chapter whose derivative is u prime over u? Yes, it is the logarithmic function, ln u. Let me remind you by this. Recall, note, this note. Ln u is derivative, its derivative is u prime over u. By this way, we can deduce that an integral of u prime over u, it will be ln what u. Usually we put absolute value, but we know here we have, this is positive, and since ex is positive for any x, plus 1, it's also positive. So it will be ln ux between 0 and 1. Let's continue there. It will be ln 1 plus ex, we just replace ux by its value between 0 and 1. And as you know, we work on indefinite integral by substituting first the upper limit, then minus substituting the lower limit. Ln 1 plus e to 1 minus ln into 1 plus e to 0, which is ln 1 plus e minus ln 1 plus 1, which is 2. We can leave it like this, or you may, as a property of ln functions, it will be ln 1 plus e over 2, and this is the last result, which is a constant number. The last example I would like to do it with you is integration, let's say, from 0 to 2 of x minus 5 e, let's say, 2x plus 1 dx. Be careful about this example. If you try to calculate it using the previous idea, if you think about 2x as u, the derivative of 2x plus 1 will be 2. It's totally different from this. In this case, there is a rule usually used for calculation of such cases or examples. It is, yes, we may use integration by parts, using integration by parts. As you know, if we let this to be u and this we let it v prime, integration by parts, let me remind you by it, uv prime dx, it will be uv minus integral u prime v dx. According to this rule, we can continue by let u equal x minus 5, then u prime it will be 1, and v prime equal e to x plus 1. Here we don't, to get v we integrate, and as the part 2 says, it will be v will be 1 over 2 e to x plus 1. Okay? Now, let's apply directly the integration by parts rule. uv, this is u and this is v. It will be x minus 5 times e to x plus 1 over 2. Integrated between 0 and 2 minus integral u prime v. This is u prime, which is 1 times v, which is half. We just put half outside to get e to x plus 1 dx, sure, between 0 and 2 again. We can calculate this easily. It will be, first we substitute 2 as you know, then we substitute 0. It will be 2 minus 5 times e, 2 times 2, 4, plus 1 e5 over 2 minus, substituting 0 here, you get minus 5 e, here we have 0 e to 1 over 2 minus half. The integral now of e to x plus 1, it will be half 1 over 2, 1 over a, it's like 1 over a, e to x plus 1 between 0 and 2. Okay? After that, we can calculate this. It will be minus 3 over 2 e to the 5 plus 5e, all of it over 2, since we have the same denominator. As you see, this is the result of the first part. The second part will be minus half, or minus directly 1 over 4 into e, replacing first 2 to get e, 2 by 2 plus 1, which is e5, minus e to 1, which is e. At the end, we can simplify this and to get the last result. Okay? I would like to tell you that there is another way without using to calculate this integral without using integration by part, which is quite simple, direct, and you can use it in the official exams. This way is called second method, or second way. We call it tabular integration. Again, let me write down the given, which is x minus 5 e to x plus 1 dx. Where we use this method, we use it usually when we have a polynomial here and exponential function here. From its name, we make a table, small table. Here we make derivative, and there we make antiderivative. We make derivative, first of all, we write down the polynomial here and the exponential expression here. Okay? As you see from this title, we should first make derivative of this each time till we reach 0 at the end. When we get 0, we stop there. The derivative of the first, of this one, derivative of x is 1, and the antiderivative of this is 1 over 2 e to x plus 1. Okay? The next step, we said that we must make derivative till we reach 0 answer. Derivative of 1 is 0, and the antiderivative of this, it will be half times antiderivative of this part, it will be 1 over 2 e to x plus 1, which is 1 over 4 e to x plus 1. What should we do in the next step? Here we multiply by plus, minus, till we end. Then, after that, we just multiply this term by that term, the next term on the right side, we multiply it, then minus this term times that term to get the needed result. Thus, then, integral from 0 to 2, it will be of x minus 5 e to x plus 1 dx. It will be what? This term times that term, it will be x minus 5 times, don't miss the sign, and this sign is plus, doesn't change the answer. So it will be e to x plus 1 over what? 2. Between 0 and 2. Again, minus 1 times that, so it will be minus 1 over 4 e to x plus 1. Again, between 0 and 2. And as you see, we get the same result as this result. And then we get the same answer at the end. It's quite simple. It's allowed to apply it in our official exams. Don't miss. We use it only if we have a polynomial multiplied by exponential function in this form. Derivative, antiderivative, we make derivative till we reach 0. Don't miss these signs, plus, minus, and we multiply this by the right side, the right lower side, till we get the same result. Okay, that's it for today.